In the previous video, I introduced the ideal gas law, which said that pressure times volume equals the number of moles times the gas constant times temperature. Now, the first thing that we need to kind of discuss is the fact that an ideal gas doesn't truly exist. However, there are many gases out there that behave somewhat ideally, some more than others. Okay, so we need to kind of define what an ideal gas is. Okay, the first property of an ideal gas is that the volume of the gas particles is negligible. Okay, and that's pretty typical for most gases when you think about it. Particles, they're usually composed of atoms, if not small molecules. And if you consider the fact that if you have a container with these particles in it, that the actual volume of the particles themselves, and I'm talking about the atoms or the molecules themselves, is going to be very, very small compared to the overall volume of this entire container. Okay, so basically what this is telling us is that most of the space inside of the container is empty. Okay, and the particles themselves are no way subtracting from the overall volume of the container. Now, the second property of an ideal gas is that gas particles have no affinity for each other. Now, this is where you can't really have two particles that have no affinity whatsoever. But there's many of them that actually are a pretty close approximation of this. I mean, when you think about it, for a gas to be a gas, you have to overcome the intermolecular forces holding the molecules together. And frankly, if a gas is in the gas phase, then those particles probably didn't have a very strong affinity for each other to begin with. Okay, so what this means is that if I'm dealing with two particles of a gas, and let's say they should happen to collide, they're going to just bounce off each other. Okay, they're not going to actually stick together or anything like that. All right, now again, like I said before, there is no such thing as an ideal gas, but the smaller the gas is, or I should say the smaller the particle of the gas, and the weaker the intermolecular forces, the more ideal it's going to behave. Now, another thing that I want to mention here is that the ideal gas law is very different from the gas laws that we looked at before, in that the units that we use for each one of the values that we plug into this equation have to have a very specific unit. And that arises from the fact that the gas constant has very specific units. So we said earlier that the gas constant is 0.0821 liter atmospheres per mole Kelvin. Okay, so what this tells us is that pressure has to be in atmospheres. Volume has to be in liters. The number of moles, of course, has to be in moles. And the temperature has to be in Kelvin, which is what we saw with the gas laws before. Okay. The other thing I want to point out about this equation is notice that there's no ones or twos attached to each one of these variables. Unlike the gas laws that we saw in the previous video, the ideal gas law does not relate an initial set of conditions to a final set of conditions. Okay, it describes a given set of conditions. Okay, so you wouldn't use this to try to figure out, what's going to happen if I increase the temperature of this gas to some other value. Instead, it's going to look at a given set of conditions. You're going to plug those values in, and you can calculate for any of the other variables, supposing that you have all the rest of them figured out. All right, so the ideal gas equation is going to be very useful to us because you can see here it allows us to relate several different parameters to one another for a gas. Okay, now there's a couple of different really interesting applications of the gas law beyond just being able to calculate for one of these values. One of them involves, first of all, assigning a set of conditions as being what we call standard. Okay, we call this standard temperature and pressure. Okay, or STP for short. Okay, so STP is a pressure and temperature that we have all agreed is going to be standardized. Okay, so the standard temperature is defined as 0 degrees Celsius, which is the same thing as 273 Kelvin. Our standard pressure is defined as 1 atmosphere. Now, the significance of this, first of all, it allows us to kind of try to compare apples with apples when we're talking about one gas versus another gas. If we can all agree that they're under the same standard conditions, that makes that comparison all the more useful. But also, let's go back to our ideal gas equation. Okay, and what I'm going to do here is I'm going to rearrange this equation just a little bit. I'm going to divide both sides by pressure. Which gives us V equals nRT over P. Then I'm going to divide both sides by N. And I get V over N equals RT over P. Now, V over N is the volume per mole of the gas. So what this allows us to do is to predict, from a given volume how many moles of a gas are present, or predict what volume a certain amount of gas is going to occupy. And all we got to do here is plug in our values for temperature and pressure. So let's say we assume that we're dealing with things at standard temperature and pressure. Okay, so we plug in our value for the gas constant. Oops. Okay, it's 0.0821 liter atmospheres per mole Kelvin. Okay, the temperature we said was 273 Kelvin. Okay, and then the pressure was 1 atmosphere. We can go through here and look at the units and see that Kelvin cancels out, atmospheres cancel out, and we're left with liters per mole. Okay, and we do the calculation, we wind up with 22.4 liters per mole. Okay, we call this the molar volume of a gas. And what this serves as is essentially a conversion factor, because we can now say that there are 22.4 liters of an ideal gas. I'm sorry, let me restate that. An ideal gas, when you have 1 mole of it, is going to occupy 22.4 liters. So if I have 22.4 liters of a gas, that tells me that I have 1 mole of that gas. Okay, or we can look at it as if I have 1 mole of a gas, that's going to be equal to a volume of 22.4 liters. So again, conversion factors can be created from this. Okay, and which version we use of this is going to be largely dependent upon what we're trying to calculate. But these molar volume calculations can be very, very useful. And just as kind of an aside here, 22.4 liters is about 5 gallons or so. So if you've ever seen one of those 5-gallon paint buckets or something like that, they would hold 1 mole of a gas. Now, another interesting application of the ideal gas law involves doing a calculation for density. Okay, and as we know, density is equal to the mass of a substance divided by the volume that it occupies. And for the most part, when we're talking about solids and liquids, the density is usually reported in grams per milliliter. But for gases, it's typically going to be grams per liter. Okay, and that's because gases are far less dense than solids and liquids. All right, so how does this factor into what we're talking about with the gas law? Well, let's look at the ideal gas law again. PV equals nRT. Now, before we go any further, I want to pay attention to this variable for the number of moles. Now, if you think about molar mass, it's always measured in grams per mole, okay, which means the molar mass is equal to the mass of the substance divided by the number of moles. Well, if we were to rearrange this a little bit, we find that the number of moles is equal to the mass divided by the molar mass. Okay, so I'm going to plug that in for N. So we have PV equals the mass over the molar mass times RT. All right, the next thing I'm going to do here is I am going to divide both sides. Actually, no, let's multiply both sides by the molar mass. So we wind up with the molar mass times the pressure times the volume equals the mass times the gas constant times temperature. Okay, and then I'm going to divide both sides by V. So we get MRT over V on the right-hand side. Now, I'm going to write this a little bit differently. So what I'm going to do is I'm going to group together the M and the V on the right-hand side. And also, for the sake of just convention, I'm going to put the P in front of the molar mass symbol. So we have PM equals M over V times RT. And then we're going to divide both sides by RT. And we get M over V. Well, what's so important about that? Well, it's a mass over a volume. It is, by definition, density. Okay, so we can actually calculate what the density of a gas should be. So let me write this out again. So we get P times the molar mass divided by RT equals D. Now, this is interesting and all, but it's not the most the most useful thing that we can do with this equation. I'm going to write this again now, and this time I'm going to solve for the molar mass. So the molar mass then is going to be equal to dRT divided by P. Okay, the reason why this is significant is because being able to figure out the molar mass of a substance is one of the most useful ways of identifying what that substance is. So let's say I have an unknown gas. Well, I can store that gas at a particular temperature and a particular pressure of my choosing. Okay, and then I can measure its density. I don't need to know what it is to measure its density. It's a little tricky when we're dealing with gases, but it's doable. What you need is this large round flask, and that flask is going to have a volume of 1 liter. And then that flask needs to have two ports, one on either side with valves on them. That can attach to a hose of some sort. And what you do is you take this unknown gas and you flush that through this container here until you're satisfied that the entire contents of the container have been replaced with this unknown gas. And then all you got to do is turn these knobs here to close everything off, and then you can put this whole thing onto a balance. Okay, and then you can measure the mass. So you can experimentally determine the density. You can define the temperature and the pressure. And if you can do all these things, you can find out the molar mass, which is a very clever way of finding the molecular weight of a compound and identifying it.